All right, let's look at these exercises from 6.1. So 6.1 is all about just telling you about relations, like what are relations, right? How do they work? What kinds of things go on with relations. And where we're eventually going to get to is functions, but relations are a little bit broader, right? I mean, you notice that with relations, it's really just a subset of the Cartesian products, which is kind of how we can define it, right? So we could take the Cartesian product of any two sets, right, and come up with a subset of those and say, well, that's a relation on that set, right? So, and in fact, there are some relations where you could have, they're not as restrictive as functions in many ways. So let's look at this question right here, right? So let's look at this first exercise up here. Suppose A is the set 1, 2, 3, and B is the set ABC. It says, is the ordered pair A1 in the Cartesian product of A cross B? And then we can list all the elements of A cross B. So one thing to think about is, well, what is A cross B? Can I say that A1 is or is not in that? So let's look and actually define A cross B. Let's go kind of way back to what it says in the text. If I have two sets A and B, and the Cartesian product A cross B is defined as the set of all, well, we could say A comma B, and notice that this A is not the same as the A that we're talking about here, right? Such that A is an element of A, and that's kind of weird, B is an element of B, right? So if I look up at, what I'm actually looking at, I'm trying to find, right? Well, let's remember that A is the set 1, 2, 3, and that B is the set ABC. All right. Well, right, I want to see if A comma 1 is that an element, right, of A cross B, right? And remember the element, the element of operation. This is a relation that we define on sets, right? Well, notice that A would have to be a set of this set A, right? And that 1 would have to be a set of the set B, right? Sort of like how we define the Cartesian product of A and B. And in fact, no, right? This is not true, right? So, no, right? Let's say A1 is not an element of A cross B, right? And so what are the elements of A cross B, right? Maybe we want to figure them out, right? So all we have to do is look at our definition that we sort of like defined in the chapter. I need to find everything in A and B, right? And I kind of just like pair them up, right? So this is everything in there, right? So I've got 1A, right? I could have 1B. I could have 1, right, C. And then notice I pretty much do the same thing with the 2's, 2A, 2B, right? Then I've got 2C. C, and I'm just doing this in a systematic way. And then finally 3A, 3B, and 3C. And that's our those are all the elements in our Cartesian product, the set of all Cartesian products here for A and B, right? And so notice that this set right here, 1A, looks really similar, or this thing looks really similar to this, but they're not equal, right? Because when we're talking about these relations on sets, right, and we're talking about ordered pairs, the order matters in ordered pairs, right? And remember, when we have like sets, if I had a set of elements A and 1 and another set with the elements 1 and then A, those sets are the exact same set. Those sets are equal to each other, right? But when I'm looking at ordered pairs, it matters what's in the first place, right? And it matters what's in the second place, right? If I had if I have two, well, we'll define this, right? I think this actually might be early on in the book, but if I have an ordered pair A1, A2, right? This is equal to B1, B2, right? If and only if A1 equal B1 and right A2 equal B2, right? This, right, is what it means for two ordered pairs to be equal, right? The first elements and the second elements have to be equal to each other, right? Then we could say that they're the same. So you notice in this case that's not true. So, all right, let's look at the second thing that's up here, right? So this says, notice that the composition R compose S is impossible, or, right, more properly, I guess it's empty. So why? Well, notice that if we're going to take R and compose it with S, what we would have to do is go from this set first, right? So I start in this set that I'm drawing, right? And then I'm going to go over to this set, right? So this is my S, right? And then if I'm going to compose with R, that means I would have to go from this set that I'm in, right, to, you know, to this set, right? Because it goes from this 1, 2, 3, 4 set to this A, B, C, D set. But, I mean, this S composition goes from the A, B, C, D set to the W, X, Y, Z set, right? So it doesn't make sense, right? I can't perform R because there's no element 1 in the set S. There's no element 2, 3, right? None of those elements are in the set, right? I would need 1, 2, and 3 to actually perform that. So in this case, right, it's empty, right? I can't perform it, right? Now it says, what is the only pair in the composition S compose R, right? So notice for this one, right, when I go R, 1 goes to A and C, 2 goes to D, then 3 goes to C and D. Well, notice I've gone from 1 to A, and then when I do the S, right, composition, right, this A goes to Y, right? Right? So the only pair in this composition is the pair 1 comma, y. Right? That's it. Because notice that A goes to C, and then 2 and 3 go to C and D, but C and D don't go anywhere in the S relation, right? So the relation S doesn't take C and D anywhere, right? So if I compose the two relations, the only thing I'm going to get is to go from 1 to A and then from A to Y, right? So A is the only intermediate value in there. And that's pretty much it.